So here we are, arrived at the point where we can model the motion of this Gaussian pulse using recipe 1 with dispersion. So the starting point is this function of x at time equal to 0 with this Fourier transform as we have used before. And we also know that at each time t, the k component rotates at e to the I omega t, where omega here depends on k. And in fact, omega of k is given by this equation here. And we note that with epsilon equal to 0, that is with this term here equal to 0, we get back to a linear relationship between omega and k, so this is the case of no dispersion. Anyway, with dispersion, we've got to substitute this function of here of omega of k into our equation here. So this is now the Fourier transformed wave over all k and t. And to find this motion of the wave back in real space, we have to do the inverse Fourier transform of this. And you can imagine this is fairly horrendous. We've got an e to the I t, and the omega of k here is given by this thing in the square root. And so this really has to be done numerically. Anyhow, we can do this inverse transform numerically, and this is the result we get. We can see the high frequency components stretching out ahead of the initial wave front. And again, we see spiraling behavior in the Fourier domain. It looks sort of, qualitatively similar to what we had before, but the speeds of rotation here are no longer linear with k. They are given by this relationship here. Let's now deal with this wave. This is a modulated Gaussian. So it looks like this. At time equal to 0, we have a cosine of cos k naught x. This cosine wave would be infinite in extent, extending from negative infinity to plus infinity on the x-axis. But we're multiplying it by a Gaussian, and this truncates it to give us this shape here, a Gaussian wave pulse. In Fourier space, taking the Fourier transform of this, we've got a cosine multiplied by a Gaussian, so we get the convolution of the Fourier transform of these two functions. So here is the Fourier transform of the cosine. It's two delta spikes, one at plus k, one at minus k naught. And that's convolved with the Fourier transform of the Gaussian, which is another Gaussian. So what this leaves us with then is two Gaussians, one at centered around minus k naught and one centered around plus k naught. And the width of these Gaussians, if you make it wider in real space, they become more narrow in k space and vice versa. So if we now watch this wave propagate, and let's look at the real space first, what we see is that this Gaussian envelope moving at a speed that is different to the ripples underneath. Now if you remember in the case with no dispersion, everything moved at the same speed, the wave did not change shape. But now with dispersion, different frequencies travel at different speeds, and so we have this behavior here where the shape of the wave is not changing. So unlike the case where we had a wide range of frequencies, in this narrow band example, we have a situation where the envelope is basically sticking together, but there are two different velocities involved. There's a velocity of the envelope and the velocity of the ripples underneath the envelope. If we look at the behavior over here in Fourier space, we're starting off with the two Gaussians, and they rotate in opposite directions in the complex plane, and they spread out as they rotate. So we know that omega and k have some relationship with each other. It is no longer linear. We can't tell that by looking at this animation, though. If you look at the case where there is no dispersion, it looks pretty similar. Okay, so what we see is a pulse envelope that goes a different speed to the fast ripples underneath the envelope. The ripples are slower. One way of saying this is there are two different kinds of wave speed, and I'm going to name them now. I'm going to say, what are they? Well, the speed of the envelope we're going to call the group velocity. The speed of the ripples underneath we're going to call the phase velocity. And in the next video we're going to derive what these two velocities actually are. Now you may wonder how useful this definition of group and phase velocity is going to be, given that we're dealing with a specific case here of a narrow-band multi-frequency wave, that is, a wave that only occupies a small range of k values or omega values. Well, it turns out this corresponds to a really wide range of systems that you're interested in engineering, where you're transmitting waves in optical fibers or in radio waves. This actually is useful for a lot of different situations, and indeed even in a situation where you may have a range of k values or omega values that span a wider range of Fourier space, you can always divide that up into smaller bands and treat them as a narrow wave packet in it with a specific and restricted range of frequency values.